Learn like a pro.
Hey everyone, got a chemistry or material science exam on the horizon? Well, you've come to the right place. In this explainer, we're going to break down the huge differences between pure metals and, well, their superpowered cousins, alloys.
Okay, let's kick things off with a simple question. Why is it that you can bend a paperclip so easily, but you can't even dream of bending a giant steel beam with your bare hands? I mean, they're both metal, right? So what gives one of them all that incredible strength? To figure that out, we've got to zoom way in, all the way down to the atomic level.
And to get that answer, we really need to understand what makes a metal, well, a metal. It all boils down to this really cool idea called the sea of electrons. So, picture this. In any piece of metal, each atom basically lets go of its outermost electrons. These electrons are now totally free to just roam around, creating this moving cloud, or a sea of electrons. And the atoms they left behind? They're now positive ions, all arranged in this super neat repeating pattern we call a lattice.
Now that crazy strong attraction between the positive ions and that negative sea of electrons, that's what we call the metallic bond. And seriously, you can think of it like an atomic-level superglue that holds the whole thing together in what's called a giant metallic lattice. And trust me, this bond, it's the key to understanding literally everything else we're about to talk about.
Okay, so let's take a look at how this all plays out in a pure metal, where every single atom is exactly the same size. It's like a world of perfect, beautiful uniformity.
In a pure metal, those positive ions line up in this incredibly regular, orderly pattern. Just imagine perfectly stacked layers of identical marbles, you know? They form this flawless, perfect grid.
And that perfect structure, it explains exactly why pure metals act the way they do. When you put some force on it, like when you're bending that paperclip, those neat layers can just slip and slide right past each other. There's almost no resistance. The sea of electrons keeps the whole thing from falling apart, but the layers themselves can move around.
This whole sliding action is exactly what makes pure metals malleable. It's how someone can take a chunk of gold and hammer it into a super thin sheet of gold leaf without it just shattering into a million pieces. The layers just slide into their new spots. And for the very same reason, pure metals are also ductile. This is the property that lets us stretch something like copper into all those thin wires that are absolutely essential for our electronics. And yep, you guessed it, it's all because those layers of atoms can just slide past each other. But you know, sometimes being easy to bend isn't what you want. What if you need something that's incredibly strong, something really rigid? Well, this is where humans got clever. We started engineering materials called alloys. So what's an alloy? It's not a pure element. It's actually a mixture. We take a main metal and we intentionally mix in atoms from other elements. And here's the critical part. These new atoms are a different size. And that one simple change, it completely messes up that perfect, orderly grid we saw in the pure metal.
Let's go right back to our marble analogy. Imagine trying to slide those layers of marbles, but this time you've tossed in a bunch of different sized pebbles or ball bearings. See? The layers can't slide smoothly at all anymore. They get jammed up. They resist that movement.
This atomic-level traffic jam is exactly what gives alloys their awesome properties. That disruption makes them harder, stronger, and way less malleable than pure metals. You need a much bigger force to get those layers to even think about moving.
And this basic idea, messing up perfection to create strength, has completely reshaped our world. It lets us create custom-made materials for really specific, demanding jobs. I mean, this technique literally defined whole periods of human history.
So let's look at steel. This takes us right back to our first question about the paperclip and the beam. By adding just a tiny bit of carbon into the iron lattice, we get steel, an alloy that's strong enough to build skyscrapers, massive bridges, basically the entire framework of our modern cities. Or how about bronze? When you mix tin with copper, you get a material that's way harder and more durable than just pure copper. This discovery was so huge it kicked off the actual Bronze Age. It totally transformed tools, weapons, even art. And this shows we can add other properties too, not just strength. If you add an element like chromium to steel, you get stainless steel. That chromium creates this protective layer that stops it from rusting, which makes it perfect for things like surgical tools and, the forks and knives we use every single day. All right, that was a lot to cover, right? From the sea of electrons all the way to massive bridges. So let's wrap this all up into a neat little summary. This is going to be perfect for your exam review. Okay, here's the ultimate side-by-side. When it comes to hardness, yeah, alloys are the clear winner.
Pure metals, they have one single short melting point. But alloys, they melt over a range of temperatures. But look at conductivity. They're both good conductors. And why is that? Because they both still have that sea of mobile electrons to carry a current. And as for why they don't dissolve, well, those metallic bonds are just way too strong to be broken apart by your average solvent.
Ready for a quick quiz to see if it all stuck? Let's do it. Question 1. Why are pure metals such good conductors of electricity? Think about what's actually moving around inside that metal structure.
Okay, question 2. What's the main difference in the structure when you compare a pure metal and an alloy? That marble analogy should really help you out here.
Number 3, and this builds on the last one. Why does that structural difference make an alloy so much harder than the pure metal it's made from? What is it stopping from happening?
All right, question 4. Can you name an alloy that's specifically designed to resist corrosion? We talked about one you probably use in your kitchen every day.
And for the final question, if both pure metals and alloys are good at conducting electricity, what one crucial feature must they both share inside? Yep, it's that sea of mobile electrons, the absolute key to metallic bonding. You've got this. Good luck on your exams.